In this video, we want to consider important ideas of UKMT Junior Kangaroo and 4 important ideas: caseworks in counting, analyzing blocks, small examples and find an example, ratio of areas, and speed. And we want to solve related problems of BMO, British Mathematical Olympiad, AMC American Mathematics Competition, and these two are the most prestigious exams, and also related problems in HMMT, Harvard, MIT math tournament. So from these 4 ideas, for example, from first idea, caseworks, these problems of junior Kangaroo 2022, 2021, and also problems of 2019 here, problem from AMC, problem from HMMT, small example, this problem from junior Kangaroo 2021, BMO round 1, round 2, ratio of areas, and here speed problems, which is also useful in AMC. So let's start from first idea: caseworks, counting, analyzing, and blocks, and other ideas. Okay, let's solve problem 25 of Junior Kangaroo 2022. It says I gave both Ria and Sylvie a piece of paper. Each piece of paper had a positive integer written on it. I then told them that the 2 integers were consecutive. Ria said, I don't know your number. Then Sylvie said, I don't know your number. Then Ria said, oh, I know your number. Which of these could be the integer on Ria's piece of paper? This problem related to logic, and here we know the numbers are x plus 1. At first, they know their numbers are consecutive. When Ria said, I don't know your number, means number of Ria is not 1. Okay, so for example, suppose Ria doesn't have 1, because if Ria has 1, because they are consecutive positive integer, then Sylvie has 2. And now we know the number of Ria is at least 2. Now when Ria says, I don't know your number, then Sylvie understands that the Ria doesn't have 1. Now, here, if Sylvie has 2, then she knows that Ria has what? Because she knows that Ria doesn't have 1, so Ria has 3. So Sylvie doesn't have 2. Sylvie also doesn't have 1, because then Sylvie knows that Ria has what? Sylvie can Sylvie has 3? Can Sylvie have 3? Because if 3, then here you can have 2 or 4. So here we understand Sylvie has at least 3. Then Ria said, oh, I know your number. So it means what? If Ria has 2, he knows that Sylvie has 3. Okay, Ria knows that she says, I know your number. So if Ria has 2, it is okay, because she knows that Sylvie has 3. If Ria has 3, she knows that Sylvie has 4, because Sylvie cannot have 2. 3, okay. If Ria has 4, then it's 3 or 5. So, and 2 and 3. Ria has 2 or 3. And it says, which of these could be the integer on Ria's piece of paper? 2 and 3 are possible in choices. We have only 2, so the answer is B. Okay, now let's solve next problem. Problem 24. The non-zero digits P, Q, and R are used to make up the 3-digit number PQR, the 2-digit number QR, and the 1-digit number R. The sum of these numbers is 912. What's the value of Q? Okay, it says the sum of these numbers. So first one PQR, next one 2-digit number QR, the next one is R, equal to 912. So first one PQR is R plus 10Q plus 100P plus R plus 10Q plus r equal to 912. Now here we have 100p plus 10q plus 10q, 20q plus r plus r plus r plus 3r equal to 912. And PQR are non-zero digits. And it wants only Q. So here we should consider cases. Because it is 100p, when we want to consider cases, we want to see that p is at least what? For example, if p is 1, it is not possible, because then we want to create 812. And with q and r, let's see, it is at most what? 100p plus q is at most 9. 20 times 9. R is also at most 9. 3 times 9. So 20 times 9 is 180. 3 times 9, 27. So it will be 100p plus 207. And then 100p is at least what? 912 minus 207. 12 minus 7, 5. And then it will be 0, 0 minus 0, 0. 9 minus 2, 7. And then p is at least 705 divided by 100. So it will be 7.05. If less or equal, p is integer, so p is at least 8. So we should consider two cases. And also, let me tell you something. It is even, it is even, it is even, so this one also should be even. So let's consider first p is 8, case 1. So 800 plus 20q plus 3r equal to 912. Okay, here we subtract 800 from both sides, 20q plus 3r equal to 112. It is multiple of 4. This one is also multiple of 4, so r is multiple of 4. So r is 4r prime in this case. And it will be 20q plus 3 times 4r prime is 12r prime equal to 112. If we divide both sides by 4, it will be 5q plus 4r prime. I'm sorry, we divide by 4. 3r prime equal to 2 for 832, 8. And now here, let's consider cases. If q is, if we consider the remainder when divided by 3, 5q, 28 should be 1. You can use modulo if you know. But if you don't know, let's consider different cases. We know that if, for example, q at most 5, then r prime is 1. And it's good if q is 4. If we decrease q4, it will be 8. It's not possible. If we decrease it to 3, 15, 13, not possible. If it is 2, then r prime is 6, and then r will be bad, will be 4 times 6, 24. So in this case, q is 5, r prime is 1, so r is 4, and p is 8. Okay, so let's check this case first. In this case, PQR is what? PQR is 854. So if we add 854 plus QR, which is 54, plus R, which is 4, this one will be 58. 8 plus 4, 12. We have 1. 1 plus 5 plus 5, 11. We have 1, 912. It works. So 854. Q is what in this case? 5. So we found. Also, we can check case 2. Let's check case 2 to prove that there is no other answer. P is 9. So here it will be 900 if you replace P with 9 plus 20Q plus 3R equal to 912. And if you subtract 920Q plus 3R equal to 12, and Q should be 0. Because if Q is 1, it will be at least 20. And the problem says non-zero digits. Okay, so case 2 is impossible. Our answer is choice C, 5. Okay, next problem is problem 22 of Junior Kangaroo 2022. It says Andrew wants to write the numbers 1, 2, 3, 4, 5, 6, 7 in the circles in the diagram so that the sum of the three numbers joined by each straight line, like this one, this one, this one, this one, is the same. Which number should he write in the top circle? So let's see. One part is here, one part here, one here, one this one this one. Okay. Okay, one idea is to add all cases. So here we say one case is this one case this one case this one, this one, this one. And suppose it says all of them are same. So suppose each of them equal to, for example, t, sum of each part. So t here, sum here, t here, t here, t here, t. 1, 2, 3, 4, 5. So 5t equal to, we consider this one twice, 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 here and here, this one twice, but this number 3 times. Let's consider it is x, we calculate this 3 times. So we calculate 1 to 7, 3, 4, 5, 6, 7, all of them except x twice, but we calculate x 3 times. So it will be 2 times 1, 2 to 7, 2 times minus x minus 2x plus 3x equal to 2 times 1 to 7 is 7 times 8 over 2. Minus 2x plus 3x will be plus x2, and this will be cancelled. It will be 56 plus x. So x plus 56 should be multiple of 5. So if it is 2, it will be 58, 3, 59, 4. So we can cancel this case. If it is 5, 61. If it is 6, 62. So the only choice that is left is 4. And you can find an example here. So we call it double counting also. Double counting. And here add all conditions. These two ideas are so much useful in many problems. So let's consider next one. Junior Kangaroo 2022, problem 21. Problem 21. Patricia painted some of the cells of a 4x4 grid. Carl counted how many red cells there were in each row and each column, and created a table to show his answers. Which of the following table could Carl have created? So here when it says 0, it means we don't have anything on this column. But here it has 4, so it should be 4 in this row. So this cell should, from this part, should be red. From here shouldn't be red. So it's not possible. Now let's see. Zeros and 4 are good. We can decide. So let's consider here this one. It's not good, not good, not good, not good. And then here, because of these two rows, if we consider this column, 3 cells should be red, but 2 cells are left. So again, this one is bad. For this one, you say, okay, 0 similar to this, 0 similar to this. Then we have 3 here, so 3 here. Then we have 3 here, 3 here, because of we've considered these rows and this column. Now in this, for this column, we have problem because we have 2 reds, but it says 1 red. So we should select between B and D. For B and D on, and some of the, because each cell, if it is red, we count it from here and here. Some of the numbers from in rows and columns should be equal. 2 plus 2, 4, 4 plus 3, 7, plus 1, 8. It is a necessary condition. 1 plus 2, 3, 3 plus 1, 4, 4 plus 3, 7. So it's not possible. As you can see here is good. Let's find an example for this case. We can say 2, 2, 2, 2s. 1 here. 2 here. 2 here. I think it's good. 2 is okay, 1 is okay, 2 okay, 2 okay, 2 okay, 2 okay, 1 okay, 2 okay. So the answer is D. Okay, if you wanted to solve more problems like this, as I said before, feel free to send message on our WhatsApp number in the description. Problem 25 of Junior Kangaroo 2021. Sonia wants to write a positive 5-digit integers whose digits are 1, 2, 3, 4, 5 in some order. The first digit of the integer is to be divisible by 1. The first two digits are to form a two-digit integer divisible by 2. The first three digits are to form a three-digit integer divisible by 3. The first four digits are to form a four-digit integer divisible by 4, and the five-digit integer itself is to be divisible by 5. How many such five-digit integers could Sonia write? Okay, so if you write a number like this, A, B, C, D, E, A is divisible by 1, AB is divisible by 2, ABC is divisible by 3, ABCD is divisible by 4, ABCDE is divisible by 5. Now, because the digits are 1 to 5, and when we have some cases, the priority, or we should start from which case? The most restricted case. It is so much useful. The most restricted case. If we consider this condition, which condition is the most restricted one? Last one. Because it is multiple of 5, last digit should be 0 or 5. We don't have 0, so last digit is 5. So E is 5. Now let's consider this one. CD. ABCD divided is divisible by 4. Last two digits should be divisible by 4. So we conclude CD is divisible by 4. So what are the cases? D should be even, so it should be 2 or 4. If it is 2, 12 is good. 32 also is good. Let me write 12 good, 32 good. 52 we can't use 5 because E is 5. If D is 4, then 24 is good. 44 we can't use. So we have these three cases. So let's check them. Case 1, case 2, case 3. In case 1, we have A, B, C, D is 1, 2, and last one is 5. So this one is multiple of 4. This one is multiple of 3. This one multiple of 2. So because the only even numbers are 2 and 4, so B should be 4 because AB is multiple of 2. So it will be A2, 1. Here we've used 2, so B should be 4. A4, 1, 2, 5. Okay, A is the digit that is left is 3. 34, 1, 2, 5. So let's check. Is this number is multiple of 2? 34, 341. It's not multiple of 3, so it's not good. Now let's consider case 2. AB, CD is 32, and E is 5. Here, we know AB is multiple of 2, so we conclude B should be even, so B should be 4. A4, 3, 2, 5. And A is the digit that's left, 1, 4, 3, 2, 5. Again, it's bad because this number is not multiple of 3. Third case, A, B, 2, 4, 5. And now here, if we consider B should be even, and here we don't have any selection. So again, as you can see, this case is also bad because B should be even, but we've used 2 and 4, so we don't have even. Okay, so we don't have any selection here, so there is no answer. It says, how many such 5-digit integer could Sonia write? 0. The answer is E. Now we've solved 25. Let's solve 24 of 2021. It says four positive numbers P, Q, R, and S are in increasing order of size. One of the numbers is to be increased by 1 so that the product of the 4 new numbers is now as small as possible. Which number should be increased? So here, if we consider they are increasing order, so P is less than Q, less than R, less than S. And if we increase, we have 4 cases to increase each of them by 1. For example, suppose we increase P by 1, then it will be PQRS plus QRS. If we increase q by 1, it will be p q plus 1 rs, so it will be pqrs plus prs. If we increase r by 1, it will be this one. Again, it will be pqrs plus pqs. And fourth one, if we increase s by 1, it will be pqrs plus pqr. Now, the smallest one, because pqrs is in common in all of them, so the smallest one is when you multiply pq and r. So when you increase s by 1, it will be the smallest one. Here, also, we can use the small examples. For example, p1, q2, r. So it is 1, it is 2, it is 3, it is 4, and find these numbers. We will solve this in a small example part with the second solution. So solution 1 is this. Now, okay, let's solve next problem here. We've solved 24. 23. Using only pieces like the one shown in the diagram, Zara wants to make a complete square without gaps or overlaps. What is the smallest number of pieces she can use? Okay, if we count 1, 2, 3, 4, 5. So if we can tile an n by n is multiple of 5, okay? So let's check first 5 by 5. 1, 2, 3, 4. 1, 2, 3, 4. So this cell should be covered. So it can be like, for example, one case is this one. Or we can create this one. Let's see. So one case is this without loss of generality. One case 1, 2, 3, 4, 5 is this. Okay, so let's write again. One case is this one. One case is this one. One case is this one. So here, because we have corner, there are the cases. Also, we can say another case, for example, is this one. If we consider, it will be okay. And yes, let's consider these 4 cases to see can we create. If it was not possible, we will find a way to prove that it is not possible. And then we try 10 by 10. If 5 is the answer, you say 5 times 5 over 5 is 5. If 10 is the answer, 10 by 10 over 5, it will be 100 over 5, 20. So, as you can see, 16 and 8 cannot be the answer. If, for example, 15 times 15 is the answer divided by 5, it will be 75. So let's try first 5 by 5. We want to try, for example, we can say one case is this. And if you want to fill here, again, it's hard. Let's see, can we use coloring to prove it's impossible? Okay, so let's use a coloring. If we consider each tile, and if we color with black and white checkerboard scheme, there are 3 important colorings that 90% of coloring problems can be solved with them. Colorings, checkerboard scheme, general form of checkerboard scheme, increasing, decreasing, and column coloring. Here we want to use checkerboard scheme, black and white. If you want to learn other colorings, also useful in BMO. As I said before, feel free to send message to my WhatsApp number in the description and comments. Okay. So, when you color, it can be like this, or 3 blacks, 2 whites, or 3 whites, 2 blacks. We call this W, we call this, let's call this one that has 3 blacks. B, this one doubled. Now if we color, let's color, for example, without loss of generality, color this with black and white like this. How many blacks are there? Count. 13 blacks, 12 whites. So if we consider number of blacks, If we have b from these tiles, 3b plus 2w equal to 13. Number of whites, 2b plus 3w equal to 12. Now, this is even, so w should be even. It is multiple of 3, multiple of 3. So 2b should be multiple of 3, so b is multiple of 3. Okay, so if we consider cases, b can be 0, or multiple of 3, 3, or 6, or w is 0, and even 2, 4, 3 times 4, 12. They have these cases. Also, if you consider here, it is odd 13, odd 2w even. So this one has to be odd, so b is odd. So b is multiple of 3 but odd. So we cancel this. Why w is at most 4? Because 3 times 4, 12. It cannot be 6. It will be 8 or 5. Because w is even. If it is 6, it will be 3 times 6, 18, which is greater than 12. Now let's consider w. So let's replace. If b is 3, 2 times 3 plus 3w equal to 12. It is 6, so 3w 6. So w is 2. Now if we consider this case, 3b 9 plus 2, 2, 4, 13. Okay, we found how many of each types we wanted to reach contradiction. We've not reached contradiction here, but one useful way most of the time is that. Now let's consider, here we consider corner. Let's consider central cell. Because in caseworks, the most restricted case is useful. Central one is most restricted case. It can be filled like this one, central one, or if we move it, it can be also like this. If we want to have like this, it is not possible. It is not possible. So only these two cases are possible. And now, if we want to fill here, in this part, if we consider this cell, here it should be filled. But if you consider like this, it's not possible. It should be only like this, 1, 2, 3, 4 this, and then these results won't be covered here. Let's see the most restricted case. If we consider most restricted case like this, we can say if it goes like this one, it is bad. If it is endpoint, we can also use this. But here 1, 2, 3, 4, 5, 6, 7. Again, it's bad. So it cannot be endpoints. If we consider something like this, again it's bad because 4 parts are left. If it is like this, again 6 cells are left. So in all cases it is bad. So 5 is not possible. Let's prove 20 is possible. For 10 by 10, if we draw like this, and like this, let me see, 1, 2, 3, 4, 5. So let's do something. Let's create with a better way. Here we have a 2 by 5. I can create like this one and this one. Okay, so we can create 2 by 5. So if you have a table like this, and 1, 2, 3, let me draw a little. So 2 by 5, 5, 2, 2, 2. We can create all these parts, so you can create 10 by 10. If you divide 10 by 10 by 5, we want to see how many pieces are there. It will be 20. So the answer is 20. Okay, let's solve this problem of Junior Kangaroo 2021. And problem 21, it says in a particular month, there were 5 Saturdays, 5 Sundays, but only 4 Mondays and 4 Fridays. What must occur in the next month? So let's first analyze this month. Okay, so here, because we have 5 Saturday, 5 Sunday, we know the first here. If the month is 31 days, so we know 1, 2, 3, 4, 7. We have this. Again, 8 to 14, 15 to 21, 22 to 28, and 29, 31, 30, 30, 30, 31. These 3 days, we see them 5 times. So we know 2 of them are Saturday and Sunday. So for example, if it is Saturday, if it is Sunday, then this one is Monday. But the problem says we have only 4 Mondays, so it is not possible. If Saturday is here and Sunday here, then here it will be Friday. But the problem says we have 4 Fridays, so it's not possible. So we understand that this month has 30 days. Okay, so it says next month. So next month, because the months are alternatively 30 and 31, next month has 31 days. Because it is 1 to 30, 28, 29, 30. I said the boxes are 7 by 7. It is Saturday, it is Sunday. Next one has 31 days, so Saturday, Sunday, Monday, Tuesday, and Wednesday. So we have these 3, 5 times other days. Let's write 29. Other days 4 times. So let's read 5 days, 5 Wednesdays, okay? 5 Mondays, 5 Tuesdays, 5 Wednesdays. 5 Thursdays rank, 5 Fridays rank, 5 Saturdays rank, 5 Sundays rank. So the right choice is A. Okay, so if you want to solve more problems related to months and these things, like here, casework 3130, as I said before, feel free to send message to my WhatsApp number in the description and comments. It was problem 21. Now let's solve problem 20 from Junior Kangaroo 2021. In the addition, sum shown, J, K, and L stand for different digits. It's important. What's the value of J plus K plus L? Okay, so let's solve it in a new page. Okay, here is okay. The problem, different digits. So here we should start from 1's digit. 3L is 9, or 19, or 29, or 39. And these are not multiple of 3. For here, L is 13, and for greater, L is greater, but L is a 1 digit. L is a digit from 0 to 9. So from here, we conclude that L is 3. Now, K plus L is 7. K plus L plus K is 7, or 17, or 27, and so on. 37. L is what? L is 3. So 2K plus 3. It is 2K plus 3. From first one, 2K, if you subtract 3, is 4. Next one, 14. Next one, 24. Next one, if you subtract 3, 34. And K will be what? From first one, 2. From second one, 7. From next one, 12. From here, it's bad. So we consider 2 cases. Case 1, K is 2. Case 2, K is 7. Okay? If K is 2, so we've considered L is 3. K is 2, 2, 3, 2. So it is 9, it is 7, and j is 4. So here, 3j equal to 4 or 14 or 24 or 34 and so on. 34, 44, 54. These numbers are not multiple of 3. For 24, j is 8. For 54, j is 3 times that is 18. So from here is bad. So the first case, L3, K2. We don't have any 1 here, sorry. So we can't say it is 4 or 14. It should be 4, which is impossible, okay? Because we don't have any 1 here. Okay, so let's consider next case, case 7. So if we write the sum again, L is 3, 3, 3, 3. K is 7, 7, 3, 7. And J, J, J. So from here, it is 9, 17, we have 1. It is 4. So J plus J, 3J plus 1 is 4. So J is 1. Now, in this case, L, K, J are what? L is 3, K is 7, J is 1. Sum of them is what? The problem wants the sum is 11. So the answer is choice E. Okay, problem 25 of Junior Kangaroo and 2019 related to caseworks. It says the room numbers of a hotel are all 3-digit numbers. The first digit represents the floor, and the last 2 digits represent the room number. Here the hotel has rooms on 5 floors numbered 1 to 5. It has 35 rooms on each floor, numbered N01 to N35, where N is the number of the floor. In numbering all the rooms, how many times will the digit 2 be used? Okay, so if N is 1, we have what? 101, 102 to 135. If we have 2, we have 201, 202 to 235. 301, 302 to 335. If we have 401, 402, 435, if the first one is 4, 501, 502. Here we should consider blocks or cases. Look, if we calculate, in all of them we have 01 to 35. So if we see how many 2's are there, for example, A2's, so here it will be A because we have 1 in front of each one. Here A plus 35 because we have 35 more 2's in front of the numbers. Here it will be A, here it will be A, here it will be A. So the answer will be what? Will be 1, 2, 3, 4, 5, 5A plus 35. And A is what here? From 0, 1 to 0, the first one is 0, 2. Then we have 1, 2. Then we have 20, 21, 22, 2, 29. Then we have 30, the next one 32. Okay, we have 1 here, 20 to 29. We have 10 2's plus 1, 2 in one's digit, 11. And here 1. So 11 plus 1, 12, 13, 14. Okay, so the answer is 5 times A, which is 5 times 14, plus 35. 5 times 14 is 70, plus 35, which is 105. So the right choice is E. Okay, we can consider these blocks. It was a small number, 1 to 35. Sometimes, for example, we should calculate from 1 to 2, 2023 or 2016. We had a similar problem in BMO round 1, British Mathematical Olympiad, that you should use blocks. If you want to know that problem and also work on other problems, other ideas, feel free to send message or WhatsApp number in the description comments. Okay, so let's solve next one. Here we solve 25. Let's solve 24 of this year. Okay, there are two ponds at the bottom of Gabriel's garden, each containing frogs and toads. In one pond, the ratio of frogs to toad is 3 by 4. In the other pond, the ratio of frogs to toads is 5 over 6. Suppose there are 36 frogs in total. What then would be the largest possible total number of toads in the ponds? Okay, so in one pond it says 3 to 4 frogs, so 3x frogs, 4x toads, f toads. It is in first pond. In second pond it is 5, 6. So ratio of frogs again to toads is 5y, and here 6y. Then it says suppose there are 36 frogs in total. And so 3x plus 5y equal to 36. Then number of toads is what total? 4x plus 6y is what? So here if you consider cases, the ratio, and this one is multiple of 3, so it is multiple of 3. So y is 3y prime, and 3x plus 15y prime equal to 36. So x plus 5y prime equal to 12. So y prime, it cannot be 0, because if it is 0, we don't have any ratio. Y prime is 1, then 5, x is 7. If it is 2, x is 2. Okay, let's consider, it says largest possible. So let's consider different cases. In first case, x7, y prime is 1, so y is 3. If x is 2, y prime is 2, so y is 6. Now, 3x plus 5y to make sure it's correct. 21 plus 15, 36. Next one, 6 plus 30, 36. Now let's consider 4x plus 6y. 4 times x, 28, plus 6 times y, 18, which is what, 38, 46. And this one is 4, 8, plus 20, plus 36, which is 44. And we will see. Okay, the problem says largest, so we should select 46, and the answer is B. Okay, here again, look, we've considered ratios, we've considered two cases. Again, casework problem. As you can see, casework is so much useful in junior kangaroo and also for other exams. So it was problem 24, let's solve 23. There are last problems, means hardest problems of junior kangaroo. It says Sid is coloring the cells in the grid using the four colors red, blue, yellow, and green in such a way that any two cells that share a vertex are colored differently. He has already colored some of the cells as shown. What color will he use for the cell marked X? Okay, so here, because it is RB, we have four colors RBYG. This one, let's consider to see what cell is what. Okay, again, let's consider caseworks. Okay, so this cell cannot be BY, so it can be R or G. So let's show two figures in casework. When we consider one case, we should write the cases immediately after. For example, RG, we don't calculate R and then draw this. We write R and G simultaneously. Now let's consider, for example, this case is easier. It is not RBG because it has one vertex, one edge, one vertex, and it will be what? It says share a vertex, okay? So it will be what here? It will be Y. Now, all of them, look how also this one, for example, this and this share this vertex. Here, these share this vertex. Okay, so this one is not R, is not B, is not Y, so it has to be G. And again, if we consider another cells, YG, this one, Okay, this cell cannot be Y, G, B, so it is R. R, next one is what? R, G, Y, it should be B. B, Y, G, it should be R. Here, Y, G, R, it should be B. B, Y, G, it should be R. B, Y, R should be G. G, R, B should be Y. Y, B, R should be G. And then R, B, G should be Y. R, B, Y should be G. Y, B, G should be R. R, G, Y should be B. B, Y, G should be R. And okay, let's consider this case. It is B, R, Y, so it should be G. G, R, B should be Y. Y, B, R should be G. G, R, Y should be B. B, Y, G should be R. Here, Y, G, B should be R. R, G, Y should be B. B, Y, G should be R. R, G, B should be Y. Y, B, R should be G. B, R, Y should be G. G, R, B, Y. Y, B, R, G. G, R, Y, B. B, Y, G, R. So in both cases, X is R. So the answer is A. Okay, next problem related to casework is for AMC 2022, 12A. It's an easy problem for 12A. And also we had harder problems. I released full solutions of AMC 2022. 12A, you can use my video. And in that case, I explain how to solve it with casework. Next one is this problem from Harvard MIT Math Tournament. Let's solve this one. Last HMMT 2023. Again, we can solve it with casework. Problem 2, it says compute the number of ways to tile a 3 by 5 rectangle with one 1 by 1 tile, one 1 by 2 tile, one 1 by 3 tile, and one 1 by 4 tile, and last one 1 by 5 tile. The tiles can be rotated, and tilings that differ by rotation or reflection are considered distinct. So let's draw first a 3 by 5. Let's consider, for example, 3 by 5. So this one 90 and 150. I think it's okay. 90. Okay. Now next one, for example, something like this. Here 1, 2, 3, 4. Now when we want to consider cases, we have 1 by 5 tile, 1 by 4, 1 by 3, 1 by 2, 1 by 1. Which of them I said? The most important thing in casework, consider the most restricted case. Okay, which tile is the most restricted? 1 by 5. Okay, how many options, how many places do we have for placing 1 by 5? 3. And two of them are same. Can you tell me which one? Top one and bottom one. So I multiply it by 2 and also draw for mid one. So look, I draw both of them simultaneously. Do not forget, not have careless mistake. Now, after 1 by 5, which tile is the most restricted? 1 by 4. So here, 1 by 4 can be here or here or here. Okay, so we have 4 options for 1 by 4. As you can see, we select one of them, all of them are similar, and multiply it by 4. And then 1 by 1 has to be here. 1 by 2, 1 by 3, we have 2 options. So we multiply by 2, 4 times 2, 8. Here again, 1 by 4 has 4 options. Without loss of generality, we place it here and 4. And now, we can consider 1 by 3, or you can consider this cell to be filled by 1 by 1 or 1 by 2. All of them are same. So if we want to consider cases for 1 by 3, we have 3 options. Let's write this option first. And next one, let's write this option. And let's write this option here. Okay. Now in this part, 1 by 1 has to be here, and 1 by 2 here, one case. Here, 1 by 1 here, 1 by 2 here, one case. And in this case, 1 by 2 can be here or here. And we have 2 cases. 1 by 1 will be unique. Here, here, or here, here. So 2 plus 1 plus 1, 4. 4 times 4, 16 times 2, 32. 32 plus 8 here, it's 40. So the answer is 40, and we've solved this problem completely. Now let's work on next idea. Okay, so we finished previous part by Harvard MIT Math Tournament with caseworks. If you want to solve more problems from SMT, Stanford, Harvard, and other exams, prestigious exams, SUMAC, Stanford Summer Camp, which casework is so much important if you want to solve them. As I said before, feel free to send message from our WhatsApp number in the description comments. Now let's read this problem of Junior Kangaroo 2021. It says four positive numbers P, Q, R, and S are increasing order of size. One of the numbers is to be increased by 1. We've solved this with in casework. Here I want to solve with only small examples. And it says so that the product of the four new numbers is now as small as possible. Which number should be increased? Okay, because it says P, Q, R, S are positive integers and are increasing order, let's check an example. For example, P is 1, Q 2, R 3, S 4. Now it says one of them increased by 1, so it is P or Q or R or S. Okay, and then we calculate product. So here P, Q, R, S, let's see it is what, and then we calculate product, P, Q, R, S. In this case, we had P by 1, so it will be 2, 2, 3, 4. And it will be 2, 2, 4, 4 times 3, 12, 12 times 4, 48. Next part, we add Q by 1, so it will be 1, 3, 3, 4. 9 times 4, 36. It's smaller. Next one, we add R by 1, 4, 4. So 32. And last part, we add S by 1, 1, 2, 3, 5, 15, 30. And it says which of them as small as possible. So when we add S by 1. So the answer is D. Also, we solved this one in casework completely without considering any example. Let me show you caseworks. This one, PQRS. Here. Okay, and the answer was what? Let me show you. The answer was DS, solution 1. And here, solution 2 was with casework. Was with considering small example. Okay, next one. It is BMO 1, 2021, 2022. This one, 2022, 2023. I released all solutions of this. You can use my previous videos in my channel. Also, BMO 2, 2023. I solved this also in my video. You can watch that video in my channel. I solved this with considering small example and found the idea. Only for this one you need to consider a small example. But because I've not released solution of this, let's solve this one together. Okay, it says for a given positive integer k, we call an integer n a k number if both of the following conditions are satisfied. The integer n is the product of two positive integers which differ by k, so it will be a times a plus k. And the integer n is k less than a square number, so it is b squared minus k. It says find all k such that there are infinitely many k numbers. So we check a small example. K is positive integer, so the first k we should check k is 1. So n is a times a plus 1, and n is b squared minus 1. So we can say that a times a plus 1 equal to b squared minus 1. Then here, what can we do? If we add 1 to both sides, a times a plus 1 equal to b squared. In this case, it is what? A squared plus a plus 1 is b squared. Now I want to prove it is impossible. I want to find two consecutive square, for example, c squared, c plus 1 squared. Then it cannot be perfect square. Why? For example, suppose a perfect square is between 5 squared and 6 squared. So b has no choice. because it is greater than 5 squared, less than 6 squared. So I want to do something like this. So a squared plus a plus 1, which is b squared, is greater than a squared. Why? Because it is equivalent. If you cancel a squared, a plus 1 is greater than 0. And the problem says two positive integers which differ by k. So a is positive integer. And also the problem from assumption, it says k is positive integer. So from here we conclude n is also positive integer. Okay? Now, it is also less than a plus 1 squared. Why? Because a plus 1 whole squared is a squared plus 2a plus 1. If you simplify this side and this side, it is equivalent of a greater than 0, which is correct. So for k1, we don't have any choice. Let's consider k2. N is a times a plus 2, k is 2. N is b squared minus 2. So they are equal. And we can write a times a plus 2 equal to b squared minus 2. And if we add 2, a times a plus 2 plus 2 equal to b squared. And we can say a squared. Let's write a new page. Okay, a times a plus 2a squared plus 2a plus 2 equal to b squared. Again, I want to use same idea. This idea was also useful in Promise. Promise is a prestigious summer camp that is good for your CV. It's for USA. Promise, Sumac. Sumac is for Stanford. Promise, Boston University. We have also Ross and also other summer camps. Also math, a lot of summer camps like that. And here, let me and try to find it is greater strictly between which two consecutive perfect squares. Try first, pause the video and try it on your own first. Okay, so it is between a plus 1 squared and a plus 2 whole squared. Why? Because it is a squared plus 2a plus 1, which if you simplify this and this, it is equivalent that 1 is greater than 0. For this one, it is a squared plus 4a plus 4. If you simplify, it is equivalent. Like this, a squared will be cancelled. 2a plus 2 greater than 0. A is positive integer, so again, it is correct. K2. Let's check K3. If we check K3, n is a times a plus 3, and a is also b squared minus 3. Again, they are equal, so a times a plus 3 equal to b squared minus 3. So if we add 3, a times a is plus 3 plus 3 equal to b squared. Now this part, a squared plus 3a plus 3 equal to b squared. So you can find again two consecutive perfect squared. As a hint, first one is a plus 1 squared. So the next one is easy because consecutive perfect square, a plus 2 squared. Okay, so we want to prove it. A squared here plus 4a plus 4. And here it is a squared plus 2a plus 1. And it is equivalent that a plus 2 is greater than 0. And here it is equivalent that a plus 1 is greater than 0. Okay? It was what? It was K3. Let's check K4. N is a times a plus 4. After that, we will solve for general K. N is b squared minus 4. A times a plus 4 equal to b squared minus 4. So a times a squared plus 4a, if you add 4 to both sides, will be squared, and we can see it is always perfect square. So by any a, we'll reach this. For example, if a is 1, n is 5, b is 3 squared, so 9 minus 4, which is 1 times 5. If a is 2, it's 2 times 6, it's 16 minus 4, and it is 12. A is 2, and so on. So K4 is the first answer. Now we consider K at least 5, and we want to solve for general K. So these things help a lot to find the solution. We use same idea, b squared minus K. If you want to learn, if you want to know the promise problem and how can we approach that problem like this, as I said before, feel free to send message to my WhatsApp number in the description comments. Here, a squared plus ak equal to b squared minus k. So we conclude that a squared plus ak plus k equal to b squared. Because I want to place it between two consecutive perfect square, it is important that k is even or odd. Okay, let's consider first case, k is even. So k equal to 2q, so it will be a squared plus, and we know k is at least 5, so q is at least 3. A squared plus 2aq plus 2q equal to b squared. So we want to find two perfect square. Let's write it again. A squared plus 2aq plus 2q, which is b squared, is at greater than a. We want to prove a plus q squared. And let me see. A plus q plus 1 is obvious. Here, if I place this a squared plus 2aq plus q squared, so I think I should place a plus q here. And then I place a plus q minus 1 here. So this one is what a squared plus 2aq plus q squared. This one is a squared plus 2aq minus 2a, 2 times this, plus q minus 1 whole squared. Now it is equivalent. A squared 2aq will be cancelled. Q squared is greater than 2q, which is if we divide by q, q greater than 2, we said q is at least 3. That's correct. For this one, a squared 2aq will be cancelled. We take 2a to right side, 2q to left side, q minus 1 squared minus 2q. And because it says you should find infinitely many k numbers, infinitely many, so after some parts, a will increase up to infinity. So for example, if we have some good numbers after, for example, a greater than this, we have this inequality and we can't find any good number. So we can't have infinitely many good a because a increased to infinity. So here we reach contradiction. Sorry, here it is correct. So between two consecutive numbers, so we don't have any other k that is good means we have infinitely many k number. If k is odd, we write k is 2q plus 1. And because 2q plus 1 is at least 5, q is at least 2. So here we can say a squared plus ak plus k is b squared. A squared plus ak plus k equal to b squared. Here we replace k with 2q plus 1. So it will be a squared plus a times 2q plus 1 plus 2q plus 1 equal to b squared. Now here I can say it is greater than a plus q squared less than a plus q plus 1 squared. Let's prove it. For this part, it is a squared plus 2aq plus a plus 2q plus 1. We want to prove less than a squared plus 2aq plus 2a plus q plus 1 squared. Here we can cancel a squared. We can cancel 2aq. And we can cancel 1a with 1a here, so a is greater than 2q plus 1 minus q plus 1 squared. So because we have lots of a, it is constant, so we can say after some a, it is correct. Now let's consider this part. A squared plus 2aq plus q squared less than a squared plus 2aq plus a plus 2q plus 1. So a squared cancelled, 2aq cancelled, a greater than q squared minus 2q minus 1. Again, this part is constant after some k numbers. If you find, this inequality will be whole, and we can't have infinitely many k numbers because after some a, there's an a greater than a constant, We have this inequality and means b squared is between two consecutive perfect square, which is contradiction. So the only k that is good is k4. It was one application of considering a small example that is so much useful in BMO1, BMO2. I released many videos. If you want to learn how to approach problems similar to these, as I said before, feel free to send message to my WhatsApp number in the description comments, and you can prepare for BMO round 1, BMO round 2, AMC for America, USAMO, IMO, and all other parts. Next idea is ratio of areas. Okay, for this idea, we want to solve 2021 Junior Kangaroo problem 22. In the diagram, PQRS is a rhombus, PQRS, all sides are equal. Point T is the midpoint of PS, and point W is the midpoint, so we can say it's X, it is X, it is X, it is X. This one 2X, this one 2X. And what's the ratio of the unshaded area to the shaded area? Okay, for these types of problem, we can, let me draw diameter. So, if this area is Z, because the bases are equal Z, if you draw altitude is same here, because both bases are X. Okay, let me also show you the altitudes. If I extend this, the altitude will be some point like this one. Okay, for example, QH. QH times X is area of this part, QH times X area of this part, so both of them are Z. Similarly, this one is W, this one is W. Okay, so here the answer is Z plus W over Z plus W, which is 1 over 1. In for areas, we have lots of formulas. One way is you say, okay, the area for a triangle is half times, for example, base times altitude, or you can say 1 half BC sine A, or also Heron's formula. If the sides are ABC, you define S equals semi-perimeter, which is A plus C, B plus C over 2. So the area of ABC is the square root of, we call it Heron's formula. S times S minus A, S minus B, S minus C. So if we know three sides, we can easily calculate the area. And there are lots of other formulas. If you want to learn them and solve similar problem in BMO, other exams, Stanford, SMT, HMMT, Harvard, MIT Math Tournament, as I said before, feel free to send message to my WhatsApp number in the description comments. The next idea here is related to speed. Problem 22, Bryant always cycles to work, leaving at 8 a.m. every morning. When he averages 15 kilometers per hour, he arrives 10 minutes late. However, when he averages 30 kilometers per hour, he arrives 10 minutes early. What speed should he averages to arrive on time? Okay, we know speed or velocity speed equal to distance over time. For all these problems, also we have in AMC, American Mathematics Competition, we use this formula. So first it says leaving at 8 a.m. every morning. Then he averages 15. Okay, when speed is 15, he arrives 10 minutes late. So for example, let's consider time, for example. C plus or T1 plus 5 plus 10, 10 minutes late distance. When he averages 30 kilometer, he arrives 10 minutes early. So d over t1 minus 10. Then it says what speed should he averages to arrive on time. So what speed v equal to d over t1. So we should find v. That is d over t1. Let's consider it is 15 t1 from first one. Let me write in front of that. Let's move it here. It is what? So we can say 15t1 plus 150 equal to d. And here 30t1 minus 300 equal to d. Okay, so we want to get rid of this constant. 115 we multiply by 2. So it will be 30T1 plus 300 equal to 2D. And then we add 30T1 plus 30T1, 60T1, minus 300 plus 300 will be cancelled, 2D plus D, 3D. So then we can divide by 320. So D by T1 equal to 20. So here the answer is 20. So when you see problems related to speed, this formula is the most important formula you should use. As I said before, if you want to learn the rest of the ideas that are useful for junior kangaroo, UKMT, junior part, intermediate, and senior part after that, BMO round 1, which I released full solutions of last BMO round 1, also last BMO round 2. If you want to learn how to approach problems, important ideas, or what important summer camps that you can pass, like SUMAC for Stanford, Promise, Boston, and many other summer camps. If you want to participate in those summer camps to have good CV, apply university, all these things, 40-50 important ideas in each topics, combinatorics, number theory, algebra, and geometry. As I said before, feel free to send message to my WhatsApp number in the description and comments. Thanks for watching this video. Have a great day. Bye.